Okay, so in this lecture I am going to discuss shifting in the s-domain, shifting in the time domain and scaling properties of the Laplace transform. So first let us talk about shifting in the frequency domain. Shifting in the s-domain, or simply you can say shifting in the frequency domain, both are same. Okay, so you are doing the shift in the frequency domain, that is s domain. It is equivalent to multiplication by an exponent in the time domain. So multiplication by an exponential function in time domain. Now the property is as follows: if x of t has Laplace transform x of s with ROC is equal to R, then e to the some constant s naught t times x of t has a Laplace transform x of s minus s naught. Okay, so now the ROC will be with ROC is equal to R plus this s naught can be a real constant or it can be complex constant. Therefore, we will write real of s naught. Okay, that is the ROC associated with x of s minus s naught is that of x of s shifted by how much amount? Real of s naught amount it is shifted. Okay, thus for any value s, that is in R, now the value of s plus real of s naught will be in R1. Let me call this one is, this whole thing is R1. Okay, now let us prove this property. So what we are going to show is that if you multiply a function x of t by an exponential function like e to the s naught t, then it corresponds to a shift in the frequency domain. How much it is shifting? By an amount x of s minus x naught. This is shift in the frequency domain. Okay, that is in the s plane or in the s domain. Okay, now let us find out the Laplace transform of e to the s naught t x of t. Okay, to make more generality, this s naught can be complex. It can be real or it can be complex. So integral of 0 minus to infinity e to the s naught t x of t e to the minus st and dt. Okay, so either you can put a 0 minus or 0 plus, it doesn't matter. Okay, so whether you take from 0 minus or 0 plus, it doesn't matter. It depends upon what you take x of t to be. So the type of x of t that you are interested in. Okay, either you can put a 0 minus or 0 plus, it doesn't matter. It depends on the type of functions. I mean, that's what I want to say here. So 0 minus to infinity, then x of t times e to the minus of s minus s naught times t and dt. If you rearrange this, you will get like that. Now you can see that if you if you had been like this, x of t e to the minus st and dt, then you wrote this guy as x of s, right? So if you have s here, then you wrote x of s. Now instead of s, it is here we have x of s minus s naught. Therefore this would be x of s minus s naught. Okay, therefore the Laplace transform of x of t e to the s naught t is like this. Okay, so if you take this expression in this integral, after integration you substitute the limit for t. Okay, so integral of x of t times e to the minus st. For example, x of t is equal to e power minus at times u of t, then integral of 0 minus to infinity e power minus of s plus a times t times dt, then this is e to the minus of s plus a times t and 0 to infinity, t equals 0 to infinity. Now what you do, you substitute s plus a infinity minus e to the minus of s plus a times 0 divided by minus of s plus a. Now once you substitute the value for t, then finally you will end up with 1 plus s plus a. So the final expression is a function of s. Therefore this we wrote as x of s. But here after you substitute this limit and this limit in this integration, then it will be a function of s minus s naught. That is why we wrote x of s minus s naught, that is shift in the frequency domain. Okay. So that's it about this property. Then let us take some simple example based on this. U of t has a Laplace transform 1 over s. Suppose you multiply u of t by e power minus alpha t times u of t. Then you recall that property, e to the s naught t times x of t. What is a Laplace transform? X of s minus s naught. If this is plus, then there is a minus. If we have minus here, then it becomes plus x of s plus s naught. Okay, s plus alpha. So this is your x of s. So replace s by s plus alpha in this expression. So this becomes 1 by s plus alpha. You can easily find out. No need to do the integration again and again, Laplace transform integration. Okay, according to this shifting in the frequency domain rule. Now the next one is cos omega naught t and u of t. Like cos omega naught t u of t is a trigonometric function which starts from t equals 0. That means what? You have a cosinusoidal function. It exists from minus infinity to plus infinity, but you are multiplying this function by a unit step function u of t. Okay, this period is omega naught. Fundamental frequency is omega naught and this is t naught. Now the moment you multiply, then you will get like this. Sorry. Like this. Okay, so this is a truncated cosinusoidal function. Okay, so this guy has the Laplace transform of cos omega naught t times u of t. If you take Laplace transform, then this will be s divided by s squared plus omega naught squared. This result we already know. Okay, now what I am going to do, from this result I am multiplying by e power minus alpha t times cos omega naught t. Let me call this is x of t. So the Laplace transform is x of s. Now e to the minus alpha t times this guy x of t. This guy x of t. If you take Laplace transform, then it will be x of s plus alpha. What is x of s? This one. Now wherever you have s, that s will be replaced by s plus alpha. So this will be equal to s plus alpha divided by s plus alpha the whole squared plus omega naught squared. Simple calculation. So this we have already derived cos omega naught t u of t. Okay, that is s divided by s squared plus omega naught squared. Now I am multiplying this guy with the e to the minus alpha t. Now you apply the shifting in the frequency domain property, shifting the s-Doamin property, and then simply you can write down the result. What is your x of s? X of s is this, and replace s by s plus alpha. So the numerator is written like this, s plus alpha, and the denominator also we wrote like this, s plus alpha the whole squared plus omega naught squared. By the way, how does this function looks like in the time domain? We know this cos omega naught t into u of t like this, and this e to the alpha t will be like this. If you multiply these two guys, then it will be like this. So your function, it is a decaying sinusoidal, and this is your envelope where the amplitude decays, where the amplitudes decay as e to the minus alpha t. This is e to the minus alpha t. So exponentially damped sinusoidal function of time. So this is exponentially damped sinusoidal function. Function of time. So according to this rule, shifting the time domain rule, frequency domain rule, all we have to do is replace s by s plus alpha. Okay. So this gives you a new function of time, that is Laplace transform pair. Therefore e power minus alpha t cos omega naught t u of t, it gives you a new Laplace transform pair. So no need to memorize this one. Okay, once you know the Laplace transform of this, then you can find out the entire thing. So this is equal to s plus alpha divided by s plus alpha the whole squared plus omega naught squared. Okay, so we don't have to remember this formula. So this formula, no need to remember. Okay, no need to remember that. So whenever it gets multiplied by an exponential factor of this type, by an exponential factor like e to the minus alpha t, then you should be able to do that very simply. Wherever you find s, simply replace s by s plus alpha. In the similar manner, you can find out e to the minus alpha t sin omega naught t u of t. This is omega naught divided by s plus alpha the whole square plus omega naught square. We know the Laplace transform for sin omega naught t into u of t. What is this? This is omega naught divided by s squared plus omega naught squared. Simply you can find out this s will be replaced by like this. Okay, visualizing this in this fashion will be very important. Okay, when you are taking sometimes inverse Laplace transforms of functions where a quadratic exists in the denominator. For example, suppose I take this function, let's say s plus 1 divided by s squared plus s plus 1. Then how do you find out inverse Laplace transform ILT, right? So L inverse of s plus 1, it's very easily you can find out this s plus 1 like this. Then see the poles of this rational function or the roots of the denominator polynomial are complex, this one. Okay, minus b plus or minus square root of b square minus 4ac divided by 2a, you can use this and find the roots of that denominator polynomial. Okay, so these are complex, and these poles are complex conjugate. So I can write this poles as s plus alpha the whole squared plus omega naught squared like this. In this form I can write. Okay, so if you try to put it in this form, then you can decompose this denominator function into sum of two such functions, and then you can readily recognize them to be the Laplace transforms of sinusoidal functions with a decreasing amplitude. That means s plus 1 divided by s squared plus s plus 1 you can write as s plus 1 divided by s plus 1 half the whole squared plus root 3 by 2 the whole squared. You can work on this. Simply find the roots. Now if the numerator had been s plus 1 by 2, then I can write in terms of cos omega naught t. Okay, if you recall cos omega naught t, this is a formula, s plus alpha, and the denominator also s plus alpha. See, s plus alpha and square. But here I have s in the denominator s plus 1 by 2, but here I have s plus 1. So I need to do something here, modify the things. What will I do? I will put s plus 1 half plus 1 half like this. The denominator s plus 1 by 2 the whole square plus root 3 by 2 the whole square like this I can write. Now again rearrange this, s plus 1 half divided by s plus 1 by 2 the whole squared plus root 3 by 2 the whole squared plus 1 by 2 whole divided by s plus 1 by 2 the whole squared plus root 3 by 2 the whole squared. Now what is this? This is in the standard form of your e to the minus alpha t times cos of omega naught t. So if you take a inverse Laplace transform of this, then this is going to be what? E to the minus 1 by 2 t, correct? Then cos of omega naught is root 3 by 2 t. That's it. Now if you come to this guy, what is this guy? What is this? If you look at this sine formula, generalized sine formula, the numerator you have omega naught, here also you have omega naught. So, but if you look at here, in the denominator you have root 3 by 2 the whole square, but numerator you have something else. So what you do in this guy, with this guy? So what you do is 1 by 2 whole divided by s plus 1 by 2 the whole square plus root 3 by 2 the whole square. You multiply both the numerator and denominator by root 3 by 2 divided by root 3 by 2. Okay, so now what will happen? This you simplify as 1 by 2, 2 by root 3 times root 3 by 2 whole divided by s plus 1 half the whole square. Just to manipulate, okay, to bring it to the standard format, root 3 by 2 the whole square. Now this looks like e to the minus alpha t times sine omega naught t. What is omega naught? This guy. This 2 and that 2 will get cancelled. So 1 more root 3 times e to the minus 1 half t sine of root 3 by 2 times t. That's it. If you put together these two guys together, then this becomes 1 over root 3 e to the minus 1 half of t sine of root 3 by 2 times t. The whole thing multiplied by u of t. U of t. So this is your x of t. Okay, which corresponds, this corresponds to the Laplace transform of s plus 1 divided by s squared plus s plus 1. Okay, when you multiply the time function by an exponent, will come in handy not only in finding the Laplace transforms of certain time functions, but also it will be very much useful to find out the inverse Laplace transform of quadratic factors. So whenever in the denominator you find some quadratic factors, then this shifting in the frequency domain will help you a lot. It will simplify your work very easily. Okay, so whenever you have this quadratic factors in the denominator, then you may get a complex roots. Okay, so the roots are a complex conjugate, so it can easily be handled in this fashion. Okay, so the rule we have considered just now is that if x of t is multiplied by an exponential function of time, that corresponds to a shift in the frequency domain. So we have a dual rule which corresponds to shift in the time domain. So e to the s naught t x of t has the Laplace transform of x of s minus s naught. Now what will happen if you shift in the time domain, let's say x of t minus t naught, then what is going to happen in the frequency domain? So this is a dual relationship. In the time domain you multiply by exponent, in the frequency domain shift. Now in the time domain you shift, time shift, and let us see what is going to happen in the frequency domain. So that is the next property, that is time shifting in the time domain. So time shifting. So this property says if x of t has Laplace transform x of s with the ROC is equal to R, then you shift the signal by an amount x of t minus t naught, then it has the Laplace transform of x of s multiplied by e to the minus s times this t naught. So this minus sign will come as it is, there is no change, especially in the time. With ROC is equal to same region of convergence. And this property is very, very straightforward to prove it. Okay, multiplication by an exponential function in the complex frequency domain. So you are multiplying in the frequency domain, that is an exponential. Okay, that means what? Let's say you have a like this x of t, then x of t minus t naught will be like you are shifting by t naught seconds, then it will be like this. This is your x of t minus t naught. You are delaying the signal, okay, by an amount of t naught seconds. So instead of starting from t equals 0, it starts from t equals t naught. The same function is delayed by an amount of t naught. Therefore we describe this function as x of t minus t naught. Everything is delayed by t naught seconds. Okay, whatever value this function x of t takes at t1, let's say t1, then this guy takes at t1 plus t naught seconds. That is, it is delayed by t naught seconds. Now what we are saying is, given that the Laplace transform of x of t is x of s, then the delayed version of x of t minus t naught has Laplace transform of x of s multiplied by e to the minus s times t naught. Okay, so a shift in the time domain corresponds to multiplication by an exponent e to the minus s naught in the frequency domain. So delay by t seconds involves multiplication in the frequency domain by e to the minus st naught. We take tau to be greater than 0, a positive quantity. Okay, so if you take negative quantity, what will happen? That we will discuss in a minute. Now, okay, so the proof of this is quite straightforward. So we are interested in finding out the Laplace transform of this guy. Okay, so let's say what is your x of s? X of s is equal to 0 minus to infinity x of t times u of t, then e to the minus st and dt. Now if you delay the signal, then Laplace transform of x of t minus t naught, then u of t minus t naught, then this is 0 minus to infinity x of t minus t naught, then u of t minus t naught, then e to the minus st, same definition, and dt. Okay, now this u of t minus t naught is 0 as long as t is less than t naught. Okay, if t is less than t naught, then this guy becomes 0 because the argument is negative. The argument will be negative. Therefore, instead of starting from 0, let me start from t naught to infinity, then x of t minus t naught, then u of t minus t naught, e power minus st, and dt. And anyway, in this interval, this is equal to 1 from t naught to infinity. So this is t naught to infinity x of t minus t naught, e to the minus st, and dt. Okay, now let us put t minus t naught is equal to tau, then t is equal to dt is equal to d tau, and the range of integration now when t becomes when t equals t naught and then tau equals 0. Okay, so the integration starts from 0 now. When t equals infinity, then tau also equals infinity. Therefore, the integration is 0 to infinity x of tau e to the minus s. T becomes, from this, t is equal to tau plus t naught, then dt becomes d tau. So integral of x of tau e to the minus s times t naught, e to the minus s tau, and d tau. Now the integration is with reference to tau. Therefore, this is constant. You can pull out of the integration. E to the minus st naught integral of 0 minus, I forgot to put minus, x of tau e to the minus s tau and d tau. If you don't like tau, then you can change that dummy variable to t now again. E to the s t naught 0 minus to infinity x of t e to the minus st and dt. And don't you see that this is the definition of the Laplace transform of x of t, which is equal to x of s. Therefore, e to the minus s naught times x of s. Okay, so this particular rule is very, very important because it comes in very handy in finding out the Laplace transform of various typical functions that we handled like pulse functions and so on. Now let us well, one second. This is Laplace transform of x of Laplace transform of x of t minus t naught u of t minus t naught, like this. Now this particular property has very, very important. This particular property is very, very important because it comes in very handy if you want to find out the Laplace transform of some typical pulse type of functions that we already encountered. Suppose you want to find the Laplace transform of this guy. How will you find out? Let's say 0 to t and this amplitude is 1. Let me call this is x of t. So this and all you can very easily find out. Okay. Now let me consider some examples based on this property, based on this shifting in the time domain. Now let us consider a pulse function, and that pulse function duration is from 0 to d, and this is the time axis. Let me call this is my x of t. Okay, it exists from 0 to d, and the amplitude is, let me call a. Now you can always consider this pulse to be a step function of amplitude starting from t equals 0 plus another step function, okay, starting at d with a negative amplitude of minus a. Let me call this is x1 of t and this is x2 of t. If you add these two guys, then you'll get back this expression. Okay, so in this interval the value is how much? 1, and in the same interval here the value is 0. Therefore, if you add these two guys, then you will get back this portion. But what happens in this range? Here the value is 1, but here the value, sorry, a, it is a, and in this range it is minus a. If you add plus a and minus a, then you will get back this portion 0. Okay, but but if you take this region, then that is a. So here also it is a, and here it is 0, a plus 0, 0. Therefore, a pulse can be thought of two step functions. One is u of t. What is, by the way, what is this? This one is a times u of t, and this one is minus a times u of t minus d, minus a times t minus d. If you add these two step functions, one regular step function starting at t equals 0, another a delayed step function starting at t equals d. Adding up these two, you will get a function x of t. And a times u of t, you know the Laplace transform of this guy. Okay, this is not a unit step, it is a times u of t. So this is going to be a by s. Now the next one is delayed version of minus a times u of t minus d. So there is a delay. So delay means it is going to be, just now we discussed this property. Okay, it is minus a times, you put 1 over s and multiplied by the exponent minus s times d. That's it. Or you put minus ds or whatever it is. Therefore, your x of t is a pulse function like this, d and a. This is equal to x1 of t plus x2 of t. What is x1 of t and x2 of t? A times u of t. X2 of t is minus a times u of t minus d. Then if you take Laplace transform of this, then this is going to be a times 1 by s minus a times 1 by s e to the minus sd. Simply you can find out the Laplace transform. So you observe that whenever you have your discontinuities in the function and a type of pulse functions like this, they can quite conveniently handled by using the property of the time shift. So time shifting property is very, very important. Okay. Even we can take one more example also, so that we can show the usefulness of this property. Let me take I have a sinusoidal function like this. This is t naught by 2 and this is my x of t, and assume this is periodic with t naught and omega naught is equal to 2 pi by t naught. So we want to find out the Laplace transform of this function. Okay, this x of t. How do you find out? I have only single loop here of a single loop of sinusoid. So now this can be considered to be a rectangular, a regular sinusoid like this, and you consider one more sinusoid which is, this is not in the scale, sorry. like this, you put one more sinusoid like this. Okay, delayed sinusoid. Okay, now let me call this is x1 of t. What is x1 of t? Sine omega naught t times u of t. And what is this guy? x2 of t. x2 of t is equal to delayed version of x1 of t. x1 of t minus t naught by 2. Okay, if you add these two guys, then what happens? See, here I have the negative area, and here I have positive signal, and here I have positive, and here I have negative. If I add this all these terms, then this entire portion will be 0. Okay, only one survives. Who is this guy? Who is that guy? This portion alone survives. Okay, so if you add these two, this x1 of t and x2 of t, then this is what you get. Therefore, if you add the Laplace transform of the x1 of t and x2 of t, then your job is done. Okay, by using the linearity principle, we can easily get the Laplace transform of a single loop sinusoid. Therefore, the Laplace transform x of s is equal to what? No, let me write down your x of t. Single loop is equal to x1 of t plus x2 of t. What is x2 of t? x2 of t is x1 of t minus t naught by 2, capital T naught by 2. This is my x1 of t. What is x1 of t? x1 of t is sine omega naught u of t plus sine omega naught t is replaced by t minus t naught by 2 u of t minus capital T naught by 2. That's it. Okay, now this, you know what is a Laplace transform, that is omega naught divided by s squared plus omega naught squared, plus this one is same function omega naught divided by s squared plus omega naught squared, but this is multiplied by e to the minus st naught, that is s times t naught over 2. So this is the Laplace transform of single loop. Okay, so you don't have to do any integration. Okay, the advantage of knowing all these properties is that whenever you are having functions of this type, you cleverly manipulate this by using these properties. You don't have to carry out this integration again and again to find out the Laplace transform. From the properties of the Laplace transforms, from the Laplace transforms of the known functions, you can construct the Laplace transform of this kind of either a single loop, or previously we took a pulse, whatever it is. Okay, purely through algebraic procedures. So no need to go this integration again and again. So let me take one more example. So this is very beautiful example. Okay, suppose I have a triangular pulse like this, and triangular pulse function, it is 0 and it is 4 seconds and time. Now it reaches the peak value of, let's say, 8 volts. This is my x of t. Now we would like to find out the Laplace transform of this. How do you find out? By traditional method, you can write down the mathematical equation and integrate from 0 to 4 e to the minus st and dt. You can find the Laplace transform. But instead of that, you can find out Fourier Laplace transform properties and the known Laplace transform of some known functions. Now what is the slope of this guy? The slope is slope is 2. Okay, so therefore if you draw a pulse like this, then it is 2 times r of t, a ramp function. Okay, so it reaches the 8 volts by 4 seconds. Okay, so this portion we describe by a ramp function. Then you have a ramp starting at t equals 0 and reaching the value 8 in 4 seconds at time t equals 4 seconds. Okay, so this would be described by 2 times r of t, and its slope is, what is the slope? Slope is 2. Now this ramp describes the actual behavior of x of t up to t equals 4 seconds, but after this point, in this point it is continuously going, so I must arrest this growth, after t greater than or equal to 4, because I want a rectangular function. For that, what you do, you introduce a negative ramp at t equals 4 with the same slope. So the same point you introduce a negative slope. So the negative slope means minus 2 times of that, and this ramp is delayed by, see, you are starting at this point 4, therefore it is not r of t, it is r of t minus 4, delayed version. Okay, now add these two guys, then what happens, this portion will be neutralized by this guy. So if you add these two, then you will have like this, it goes up to 8, then afterwards it becomes constant. Both are neutralized and it maintains the same height like this. So that's what we have drawn here. So this is your 2 times r of t minus 2 times r of t minus 4. Now what I want is, I want to bring this guy to 0. Okay, this guy has to come back to 0. Therefore what you do, you again introduce a step function of what is the magnitude, minus 8, and this is again delayed by 4 units, 4 seconds. Therefore this is minus 8 times u of t minus 4 seconds. Now if you add these two guys together, then you will get a rectangular pulse like this. So this is 4 seconds, and this one is 8, and this is your x of t. So this is equal to 2 times r of t minus 2 times r of t minus 4 plus minus 8 times u of t minus 4. Okay, now you take the Laplace transform of this. What is 2 times r of t? 2 over s squared. What is r of t minus 4? Again it is minus 2 times s, but it is multiplied by the exponent of minus 4 times s naught, because it is delayed. What is the Laplace transform of u of t? It is s, 8 over s, but it is multiplied again by e to the minus 4 s naught. Okay, so straight away you can find out the Laplace transform of this type of functions. Now let me consider one more example. So when you are doing this kind of shift so we must be careful when you are talking about the notation for delayed time function, that if we have x of t times u of t, what is the delayed signal? Delayed signal is denoted by x of t minus t naught and u of t minus t naught. Okay, this is the proper, this one. This is the proper expression proper expression for the delayed time functions. Delayed time functions. Okay, so if you have that ramp function like this, r of t. This r of t you can write as t times u of t, right? So suppose I write t minus 1 times u of t. How does it look like? What does it mean? This t minus 1 times u of t is not a delayed function, is not a delayed function of t times u of t. Why? Because u of t has not been delayed by t minus 1. Okay, so t minus 1 times u of t would be like, how does it look like? Let's say t minus 1, this is a function t, right? Then when t equals 0, it will be sorry, when t equals 1, hold on one second. One second. Let me take t minus 1. Let's say this is my y of t. What is y of 0? Y of 0 is equal to minus 1. What is y of 1? Y of 1 is equal to 0. Therefore, my function looks like this, y of t. Then at t equals 0, it will be minus this point. Okay, it goes like this. Okay, so this is my t minus 1. This function represents t minus 1, t axis. Now multiply this guy with the u of t. If you multiply these two guys, then you will have a function like this. So this is your t minus 1 times u of t. But actually t minus 1 times u of t minus 1 would look like this. So these two are not equal. Okay, so one should be very, very careful when you are delaying the function. This is t times u of t, and this one is, it is starting at the point 1, it is t. This is t minus 1 times u of t minus 1, and this one is t minus 1 times u of t. Suppose I have t times u of t minus 1, then what will happen? Your t will be like this. This is your t. Okay, now this is your t. Okay, now you multiply this guy by like this. This is your u of t minus 1. Then if you multiply these two functions, then it goes like this. So this is your t times u of t minus 1. And again this is not equal to t minus 1 times u of t minus 1. So be careful whenever you are doing some kind of delay or advance operation. Therefore, this is not the proper delayed version of t times u of t. Okay, so we should be very careful when you are doing this kind of operations. So let me summarize these different types of delay. This is t times of u of t, and this one is t minus 1 times u of t minus 1. Let's say this point is 1, this is t, and then this one is t minus 1 times u of t, and this one is t times u of t minus 1. Okay, and this guy has the Laplace transform of 1 over a squared, and t minus 1, this one has Laplace transform of 1 over a squared times e to the minus s, and this has the Laplace transform, if you work on it, 1 over s squared minus 1 over s, and this one has 1 over s squared times e to the minus s, plus 1 over s times e to the minus s. Okay, so these three functions have different Laplace transforms. They are not the same time functions, of course. In the time domain also, they are not the same time functions. And in the Laplace transform also, in the frequency domain also, they have different Laplace transforms. Okay, so now before we proceed, okay, so that's it about your time shifting property. And the next property is delay. So this is the property of delay, and the next one is delay in the past, reverse direction. That means time advance. Till now we talked about t minus t naught, x of t minus t naught. Then let us talk about advance operation. This is delay. Now if you write like this, x of t plus t naught, that means what? Your function is moved to the left hand side. Okay, left hand side, and this operation is called advance. Okay, suppose you have a function x of t and you advance it by an amount t naught. Then what is the Fourier transform, Laplace transform of this? X of t, if you take Laplace transform, then this is x of s. If you delay by t naught seconds, then it is x of s multiplied by e to the minus s times t naught. The same minus appear here. This is delay. Now if you advance, then x of t will be x of t plus t naught. Then the Laplace transform is x of s times e to the plus s t naught. Plus sign will come. Why? The same plus comes here. Now one can ask a question, is it correct? Okay, so this is the question that we would like to ask. We must exercise caution in applying this rule. Why? When you advance a time function, what happens is, when you push part of the time function to the negative values of time, then part of the function can get lost. Okay, so if it is delayed, then the same function variations repeats. Okay, whatever we had in f of t, u of t, sorry, x of t, u of t, the same thing you'll get in the x of t minus t naught times times u of t minus t naught. But if you advance, whatever the amount you are advancing, that will be lost. Therefore whatever is left may not have a complete replica of the original x of t into u of t. Therefore when you are applying this advanced operation, we should be very careful. See, as far as Fourier transforms are concerned, if you delay or advance by tau seconds, it is multiplied by e to the j omega tau or e to the minus j omega tau without any difficulty. Okay, because Fourier transforms handled time functions which exist for negative values of time as well, but not Laplace transforms, at least for unilateral Laplace transform. So let me illustrate this by means of an example. Suppose you take x of t. Okay, so the x of t is like this. Okay, now what is the Laplace transform of this? Let me say this point is 2. This is u of t minus 2. Okay, so the Laplace transform is e to the minus 2s divided by s. Okay, so hold on one second. Let's say this is my x of t. Then what is the Laplace transform? Let's say x of s. Now let me define another function g of t. G of t is obtained by advanced version of your x of t plus, let's say 1 by 1 minute by 1 second. Okay, therefore x of t is delayed step function starting at this is a delayed step function, okay, starting at 2. Now g of t is advanced by 1 second, so it starts from 1 second. So this is my g of t. Now Laplace transform of this guy is going to be 1 over s times e to the minus 2s, and the Laplace transform of this guy is going to be what? G of t is equal to x of t plus 1. If you take Laplace transform of this, then you will get g of s. This is x of s e to the plus s, okay, because t naught here this value is 1, so you will get like this. But actually what is the Laplace transform of this? This one is 1 over s times e to the minus s, so they are not equal. So that is the contradiction that we will get whenever you are having this kind of things. So okay, so now let me consider one more example. The same example, let's say this is 2 times, and this one is x of t. X of t is equal to u of t minus 2. Now you consider another function g of t, which is advanced by 3 units of time. Let's say x of t plus 3. So how does it look like? It looks like this, but this portion will be removed because we are considering from 0 minus onwards. Okay, this portion we are ignoring. Okay, so therefore what is the Laplace transform of this? G of t is equal to x of t plus 3, then g of t is g of s times, this is going to be x of s times e to the 3 times s. What is x of s in this one? This one, if you take Laplace transform, e to the minus 2s times x of s, sorry, e to the minus 2s times divided by s. Okay, so substitute that is my x of s. Now substitute that x of s here. So e to the minus 2s times e to the 3s. So this is e to the s. This is your g of s. Okay, now from this function, what is your g of s? This is your g of t, right? So if you take Laplace, g of t is again, if you take Laplace transform, this is 1 over s. So this is not equal to 1 over s. So there is some contradiction. Okay, from the figure you got this 1 over s. Through the properties you got e to the s by s. Both are not equal. So this is incorrect expression as far as the Laplace transform is concerned. So one should be very careful when you are taking time advance. Time delay is not an issue. So whenever you take time advance, we should be very careful. If the advance does not cross the 0 line to the left hand side, then no problem. Okay, so if the advance corresponds to a situation, okay, if the advance corresponds to a situation where no portion of the original function has been truncated, then there is no problem. Okay. For example, in the previous case we consider, let's say this is 2, then u of t minus 2, then u advance by 1 unit, then this is u of t minus 1. Let's say this is g of t is like this, and x of t. Now what is the Laplace transform of this? E to the minus 2s divided by s, and this one is by g of t is equal to x of t plus 1, then g of s is equal to x of s times e to the s. Okay, now what is x of s? X of s is e to the minus 2s by s times s, which is equal to e to the s, which is e to the minus s by s. Now from this figure also, if you take Laplace transform, what is this? This point is 1. So this is u of t minus 1. Again, if you take Laplace transform, that is e to the minus s by s. These two are equal. So as long as you don't cross this point t equals 0, then no problem in the time advance operation. Okay. So as far as the rule that we talked about is primarily intended for delay at the time functions. If you advance in time function and when it crosses the 0 point, then you will be in trouble. So you will not get the correct answer. Okay. So when it is advanced, one has to take it with a pinch of salt. The next property is scaling operation. I think this is the 7th property. Okay. So what we mean by this is, if x of t has Laplace transform x of s, then this curled version x of a t has Laplace transform 1 over a times x of s by a. Okay. So here let me write down the ROC here with ROC is equal to R. Here with the ROC is equal to a times R. Okay. So the ROC is multiplied by a. So this we can easily prove it if you want. So scaling the time domain also corresponds to a scaling in the frequency domain, but in the reverse fashion. If you make events faster in the time domain, that makes slower in the frequency domain, or vice versa. But of course with a multiplying factor, this 1 by a. This is like, multiplying the amplitude. It's not an issue. Multiplying an amplitude is not an issue, but the frequency content changes. If you compress the signal in the time domain, then it has more frequency component in the frequency domain. So the proof is pretty straightforward. So you take x of a t, then e to the minus s t dt, and the limit is 0 minus to infinity. Then you put a t is equal to tau, then do the rearrangement. Finally you will end up with 1 over a times x of s by a. Proof is not very difficult. In one step you can get the answer. Okay, now this particular rule comes in handy sometimes in the numerical working like this. Okay, let me illustrate by means of an example. Okay, suppose when you have a large numerical contents like 10 power 4 or 10 power 6 like this in the Laplace transform, then this will be very useful, this property. For example, find the inverse L inverse of, let's say, 1 over 10 to the power 4 times s squared plus 10 to the squared times s plus 1. So how do you find the Laplace transform of this? So in this case, your scaling property will be very much useful for us. So what you do is, this you can write as 1 divided by 10 to the power 4 s squared plus 10 squared s plus 1. This is equal to 1 divided by s squared divided by 10 to the minus 2 whole squared, like this I can write, plus s divided by 10 to the minus 2 like this plus 1. I can write like this. Okay, that is if s by 10 to the minus 2 is replaced by s, let's say s dash. Let's say s dash equal to s by 10 to the minus 2. Then what will happen? This relation becomes 1 divided by s dash squared plus s dash plus 1. And this, you know what is the inverse Laplace transform of this. Okay, so this will be equal to 1 divided by, just now we have done this I think in this lecture and one of the previous lecture, 1 by 2 whole squared plus root 3 by 2 the whole squared. But in the numerator I don't have root 3 by 2, so let me introduce root 3 by 2 times divided by root 3 by 2. So this is equal to 2 over root 3, then in the numerator root 3 by 2 s dash plus 1 by 2 squared plus root 3 by 2 whole squared. So this is equal to 2 by root 3, then sine of multiplication is there, e to the minus 1 half t, then sine of root 3 by 2 t. Okay, now we have assumed s dash. What is s dash? S dash is equal to s by 10 to the minus 2. So we know the property x of a t becomes 1 over a x of s by a. Okay, therefore in the s domain you have s divided by 10 to the minus 2. So therefore in the transform domain you multiply by the same factor 10 power minus. So wherever the t is there, the t should be replaced by 10 to the power of minus 2 times t. So therefore 2 by root 3 times e to the minus 1 half t divided by 10 power minus 2. Okay. Then sine of root 3 by 2, t will be replaced by 10 to the minus 2 times t like this. So this is root 2 by root 3, then e to the minus t by 200. Is that correct? I'm sorry. Why did I put in the denominator? That should be replaced by 10 to the power of minus 2 times t. So this will become minus t by 200. Then sine of root 3 by 200 times t. Now one more factor we did not include, 1 by a. So the whole thing will be multiplied by 1 by a. So 1 by 10 to the power of minus 2. Okay. Is it 1 by a x of a t? Yes. One second. I'm sorry. So in the transform domain it is 1 by a. If you bring back to the time domain, then it comes to the numerator. Therefore a times x of a t is equal to x of s by a. So you replace t by a t and the whole thing multiplied by a. So therefore the whole thing will be multiplied by 10 to the minus 2. So therefore 2 divided by 100 root 3 e to the minus t by 200 sine of root 3 by 200 times t. Okay, so the scaling rule helps us to change the scale of the coefficients so that you can handle the convenient numbers instead of some complex transforms. So remember this problem we did in accordance with x of t, the Laplace transform is x of s, and then x of a t, the Laplace transform is 1 over a times x of a s by a. That means a times x of t has Laplace transform of x of s by a. That's what we want to say. Okay, so if you make the events faster in time, this is equivalent to increasing the frequency. If you scale t in one direction, the frequency it goes in the other direction. Okay, if t is replaced by 2t, then the s is replaced by s by 2. So 2t, it becomes s by 2. T by 2 becomes 2 times s. So they are now varying in the opposite direction. So if we compress the event's time, then it occurs at a faster time. So the frequency spectrum increases. So you need to encounter high frequencies. On the other hand, if you spread out in the time domain, then frequency domain gets enlarged. That's it. Okay. If you spread out in the time domain, then the frequency domain gets takes larger value. That's it. I mean smaller value, compressed. That's what we mean by. See, if the best thing we can understand is, let's say you take a sinusoidal frequency like this, then this duration, what is the, let's say this duration is 1 oh my god. Okay, so let's say this duration is let's say 1 millisecond. What is the frequency? Frequency is equal to 1 divided by 10 to the power of minus 3, that is 1000 hertz. Now what you do, so you take the cycle like this, then what happens? Then this will be 1 millisecond, this also 1 millisecond. So therefore the total duration is 2 milliseconds. Then what is the frequency? 1 by 2 times 10 to the power of minus 3, so 500 hertz. So here it is compressed. If you compressed, then if time is compressed, then you have more frequency. If you spread out in time, say you are spreading out here, spread out in time, then the frequency domain gets compressed. That means you have very less amount of frequency, by half. You increase the duration by 2 times, then frequency will be reduced by half. See here 1 millisecond, let's say this is t naught, then it is t naught by 2. Then here let's say this is f naught, then this becomes 2 times f naught, or the other way. Here t naught equal to 1 millisecond, f naught is equal to 1000 hertz, and here t naught is equal to 2 milliseconds, and f naught is equal to 500 hertz. Okay, so both are varying in the opposite direction. That's what we want to trying to say. Okay, let me stop at this point. Thank you very much.